All right, welcome back to the 11th lecture of Spatial Statistics and Spatial Econometrics. So in today's lecture, we are going to sort of start a new topic called Spatial Stationarity. Spatial Stationarity is probably the most crucial concept that we will cover in this lecture. And spatial stationarity is something that we will, as analysts, as scientists, we will have to argue out or claim scientifically before we can go on to even define a statistic like mean or variance or whatever, right? So the idea is that unless we can establish spatial stationarity, the mean, the variance, and so on and so forth, all of the summary statistics are basically cannot be defined, right? So it's the heart of spatial statistics and perhaps the most crucial topic that we will cover in this course. Okay, so stationarity in context of spatial data. Now, the first thing that we should probably, while I introduce what is spatial stationarity, I will also sort of go over why do we need spatial stationarity, right? Now, remember that we have seen figures that you're seeing on the left side of this, of your screen here, where we have data collected at three locations, U1, U2, and U3. We have discussed earlier that at each location, the data by themselves are a realization of a random variable. That is to say that at each location, the random variable x, that is the realization x, is itself a random variable, so it can take multiple values with probabilities attached to them. There is also data at location U2 has its own probability distribution attached, because we have a random variable again at location 2 as similarly at location 3, right? When we look at a realization of data at these three locations, let's say we get a sample of data at these three locations. It could be groundwater levels, it could be the the coal sample, the soil sample, and so on and so forth, right? These three values, this pair of x of U1, x of U2, and x of U3, they by themselves are a pair of a single realization of a random function that exhibits jointly distributed random variables in space, right? So we had said that random functions are basically jointly distributed functions of random variables, right? And any observation that we see is basically one realization of this random function. On the right hand side of your screen, what you see is a probability density representation, which is as a bell curve representation on the left hand side of the screen, that is x1, x2, and x3. We have a sort of a box plot representation on the right, right? So what we see here is that at location U1, the data, majority of data, perhaps the 95% of data lie within the upper and the lower bars of the box, right? So a distribution of x of U1 would look something like this. Okay. At location 2, the distribution will look something like this. So it has lower variance, it's a tighter distribution, right? Similarly, location x3, well, it turns out it's kind of a skewed distribution. There are more outliers on the right hand side of the distribution. So I have a situation which looks like this, right? And again, a much more tighter distribution for location 4, right? Now at each location there is a possibility of observing different data points along this distribution with different probabilities. When we get a sample, we get one realization of that distribution, which are marked in dark red, right? So this, sequence of 4 values that are sampled in space, U1, U2, U3, U4, at these locations are just one realization of each, of the 4 distributions from where the data are drawn at these locations, right? Now, when we conduct statistics, what we are trying to do is we are trying to use these data, right? So we have sampled, let's say, groundwater values, and we have gotten, x of U1, x of U2, x of U3, and x of U4. The dark red dots is where we have realized these values. So we have these 4 values, but we have to use these 4 values to then infer upon the 4 different distributions of, in space. If I had 1000 data points, there will be 1000 unique distribution types from where the data are, are sampled at each location. All I have is one realization in space at a given location, and I want to infer about the entire distribution at this location from this one realization, right? Ideally, what I should be able to do is that, I should be able to hold everything constant and perhaps take, 100 or 500 observations from every location, right? So here in dark red, you see these, 4 sample points, taken at two alternative instances than the dark red realizations, right? So if for these locations we are able to sample again and again and again and again, let's say 500 times, then I will likely get data that will be representative at each location of the density function from where it was drawn from, right? But that is typically not possible, right? It's not possible sometimes due to physiological reasons. Well, for example, if you are sampling coal, once you have dug the hole and you have sampled it out, there is nothing more to sample. So you really have one data point, right? Right. So if you are working with geological, data where, you are basically digging out earth for samplings, right? You basically have to rely on just one sample point at a location to infer upon the entire distribution at that location, right? So at each location we have that challenge, right? In case of, let's say, groundwater values, it can be sampled again and again, correct, right? But it is not sampled at exactly the same point. For example, the Central Groundwater Board will probably go out 3 or 4 times in the entire year, to sample groundwater from a given well. So if this is a well and you were to sample groundwater values from this well, before monsoon and then again after monsoon, the conditions are very, very different. The data that are collected before monsoon in a given year are not going to be, distributed with the same distribution, are not going to have the same distribution after the monsoon, right? So the distribution that you are trying to infer upon will itself change, at the second instance. If that happens, effectively we are stuck with the problem that we were facing with coal sampling, right? So the idea is, what do? We really have one realization at a location, but we want to infer an entire, a distribution that this, realization is drawn from. What we do is we assume that, first of all, these data are jointly distributed, so they are all jointly, they are all, the spatial dimension is sort of binding all the marginal distributions at every location, and they are all seen as a joint distribution. Second, these data are assumed or seen to be stationary, that is to say that they are all representing the same distribution, right? So if we can be sure that we are, sampling data from the same distribution at each location, right? Then what we can do is we can pool data across space and use that as proxy for as if those realizations were coming from one location, any one location, right? This is the idea of stationarity. The idea of stationarity is that the random function that we are working with, at each location, it is exhibiting the same features than every other location, right? So there is stationarity in the sense that I can use the realization of location 1, 2, 3, 4, 5, 6, 7, 8 till 100 and infer upon the density function at location 1 and at location 2 and at location 3, as well as keep going till at location 100, right? So stationarity is really about the fact that the data exhibit similar features in that region. Now, quite clearly, when I'm talking about spatial data, we can only ensure stationarity usually in a given locality. Now, what could be the size of locality, that we will see, that we will have to figure out formally, as well as we'll start with some data and try and see what this really means. But at the end of the day, we will have to ensure that we are working with the same distribution at each location, so that then we can pool observations in space, because we don't have them through time with everything else held constant. Okay, all right. So we've already talked about why do we care about spatial stationarity. Well, we want to build a statistic for a random variable at a given location or at every location that describes certain properties. So the point is, I have one realization at location 1, but I want to infer upon the mean average realization at location 1. How do I do that, right? I will basically pool the data over space and calculate the mean and allocate it to location 1 and location 2 and location 3 and location 4. But then I've assumed that the data are stationary, right? To be able to allocate that mean value, right, to each location, I must be able to I must be able to claim that the data are stationary in that domain. Okay, so the idea is that let's say I have these air pollution monitoring stations in New Delhi, right, and at a given time point, right, on a given day in summer or in winter, let's say on New Year's, on the 1st of January of 2022, I have one sample of PM 2.5 at different locations across Delhi, right? Each location by itself is a random variable, right? And if I am saying that on average, the PM 2.5 concentration in Delhi was, about 300 units, then what I've done is I've taken an average across all the stations that I found in Delhi. You see these statistics reported all the time over media and other places, right? When we are able to commit an average for the entire domain, which is, let's say, the NCT of Delhi, what we are assuming implicitly is that the data are stationary over entire Delhi region, right? That the distribution that is being represented at each location is the same across that region. Now, is it true or not? That is something for us analysts to figure out. Can we, blindly or casually float out such average statistics? Perhaps not. That's not a scientific, report, right? But once we are sort of trained in spatial statistics or spatial stationarity, we should be able to make such distinctions, right? That is the objective of this lecture. Okay, so we are really relying on multiple observations over time, right? Instead of relying on multiple observations over time, we must pool together samples over space such that the underlying conditions are the same across the data points. And when I say same, all I'm saying is that the data are stationary. I've also here said the decision to pool data over certain points is the decision of stationarity. you have to be very careful that it's a decision. It's a it's a scientific decision to make, to say that it's stationary, right? There's not going to be a way to test this statistically, right? We are not going to be able to test it using data. We are not going to be able to put it to some kind of empirical validation. We really have to make conceptual validation of stationary or non-stationary domains. There is a very nice resource from Professor Michael Perch at University of Texas. He's a geoscientist, and I think he has very good collection of literature where he discusses stationarity. I've just sort of taken a poster that he himself shared, and I want to sort of go over a couple of things about stationarity and hoping, with the hope that it will make things a little bit more clear. So what you're trying to do is you are substituting time for space, something that we have, I've tried to motivate earlier. The idea is that he is giving an example here of coring a sample from space. So you have a domain, and you go on to these locations, U1, U2, U3, U4, U5, U6, U7. So you have 7 locations, and once you have extracted Earth out of these locations, you really have a whole. So you have no other way to sample that location again, right? You'll have to probably wait 1 million years when the depositions will happen and the Earth will be filled up naturally, and then it will be probably or probably not exhibit similar properties, right? So what do we do? What do we do is that because we cannot sample at each UI again and again, that is over time, we simply pool the observations over space by assuming that the data are stationary, that is, they all exhibit same properties, right? They all exhibit properties that are linked to the same probability distribution function, PDF or CDF, at any given location. And he gives a geological definition of stationarity. So he says the rock over the stationarity domain is sourced, deposited, preserved, and post-depositionally altered in a similar manner. The domain is mappable, so you should be able to practically map the domain, right? I mean, it is not an abstract entity only, and may be used for local prediction or as information for analogous locations within the subsurface. Therefore, it is useful to pool information over this expert mapped volume of the subsurface, right? So he's talking about a rock deposition. So we can think of coal, samples, right? Now, coal which was deposited or that came about at any location, at any region in the space, perhaps went through the same processes to be formed as a block of coal in that region. And it is not a single year process. We know it's a very, very long-term process, right? So if we are able to claim that the coal formation was, happened with similar processes, over time, then perhaps we can claim the area to be stationary and pool information over space, because we can't really sample information multiple times at any given location. A very interesting term that Professor Perch is using is, he's saying expert mapped volume. That basically points to the fact that we need expert domain knowledge to be able to claim stationarity. If I'm working with coal data, I need the domain knowledge of mining, of rock, of formation, coal deposition, and so on and so forth, right? If I'm working with agricultural yield data, I probably should be taking inputs from agronomists, crop physiologists, and so on and so forth before I can, make the claim of stationarity. If I'm working with groundwater data, I should perhaps take, inputs from hydrologists, regional planners, and so on and so forth before I can make the, claim for stationarity, right? And he is giving some statistical definition that we will come to later. But there are 2 more comments that he makes. First is, stationary is a decision. It's not a statistical hypothesis that you can test, right? So it's a decision, it's a hard decision oftentimes, but we must take it before we conduct our analysis. The second thing he says that stationarity assessment depends on scale. We cannot avoid this decision, and we must make this decision, right? So we'll look at what it means by the fact that stationarity assessment depends on scale next. Okay, so in order to sort of give you an example, I've simply taken a picture of a stone wall on our campus at IIIT Delhi, right? So this picture was taken at the Research and Development Building, at IIIT Delhi. Okay, and so here is a picture. This is a spatial domain, right? So we see the spatial domain. It has a wall. It has a metal railing with different colors. There is gray. There is also some off-white color, and there is also a board which says first floor, which is in green color. And the question that I'm trying to ask is this domain stationary, right? So now I have to make a decision as an analyst. So the first thing that comes to my mind is that, of course, this domain can't be really stationary. Why? Why can't it be stationary? Well, it is composed of such different materials. First, we have these stones, right, on the wall. We have this, let's say, a metal board, which is a completely different material, has a different color, different, spatial properties, right? And we have this metal railing, which is again a completely different, object. So perhaps what I should do in order to find a stationary domain, so I'm basically deciding as an analyst, I can't take all of this. This is a very heterogeneous surface. I have to go and look at a finer location to see if I can find a stationary domain. So let's do that. So I'm going to now focus on area within this red box and try and see if that is a stationary domain. Okay, I do that, and in this red box, what you are able to see is that again there is this stone wall, right? And also there is this patch which says first floor, which perhaps is not, is sort of the aberration in this quest for a stationary domain. But what if I were to sort of, clip this out and then look at the area? So can I say that all the region within this metal board is itself stationary, and everything else, which is the stone wall, is stationary or not? So I'm going to now focus on this problem again. Okay, so I'm not only going to look at the stone wall. When I look at the stone wall, what I find is that although I have basically concrete and stones distributed over space, right? But different stones have different properties. For example, some stones have a very, very different color tone to them than others, right? So there is this stone which is sort of light brown. There is this stone which is gray in color, right? There are stones which are, there is also the very bright white somewhere, and so on and so forth. I also see some spatial gradients, right? So there is this little cut where you have this elevation change going up from a higher elevation to a lower elevation, right? So I still see heterogeneity, and I can't really see that all of these observations, if I dig out, let's say, a sample from here, and a sample from here, and a sample from here, from these three locations, I can in fact say I can pool this information together and tell you what's happening at each location. It's hard to say that, right? So we can't really claim stationarity here. But maybe what we can do is that we can probably focus on one stone on the wall and perhaps claim stationarity. So what we are going to do next is we are going to focus on one stone which to the naked eye looks quite a homogeneous surface, right? As if I can just get 10 samples from here, I can at least say what's happening on this, on this domain, on this, stone, on this one stone. So I'm going to now focus here. So at this scale, so I'm kind of zooming in, I'm changing scales, right? When I started with the first, large scale, largest scale product, which had these, meta differences, stone wall versus the metal board versus the metal railing. The hope is I can go into each of these spaces, surfaces, and maybe, claim stationarity. When I change my scale and zoom onto the wall only, I sort of think that, maybe the stones are so different that I probably cannot claim stationarity. I should probably look at one stone at a time, right? So I'm going to now try and do that with one stone. When I do that, now I'm going to try and, just draw this boundary to the stone that we are looking at. What you see is a highly zoomed in picture of a stone, right? Now on this picture, which looked quite stationary or homogeneous from a different scale, right? When we zoom in further, we are able to sort of, see that, we have this region, which is much lighter, seems to be different than the region, let's say, that it adjoins, right? I can also see a lighter region here. I can probably also see some kind of a, change here, and so on and so forth, right? So what happens is, as I keep zooming in, my understanding of spatial stationarity or homogeneous surface or something where the underlying processes would be same keeps on changing, right? So if I zoom in enough, I'm able to, figure out, here I'm claiming I can figure out 5 stationary domains, right? I can see that this domain is different from this domain here. There is another, slightly, differentiated domain here, and I have a different domain here, right? Maybe I can even sort of, figure out more, more sort of differentiated homogeneous surfaces here, right? Now what I'm saying is, as long as you give me 10 observations in domain 1, I can pool them over space and tell you what's happening on average at a given location, right? Versus if you were to give me, 10 locations from each of these domains, perhaps it would not be a good idea for me to, pool data across domains, because there seems to be something different going on in generating data along these domains. Okay, so that's the idea of stationarity, and as sort of, as Michael Perch, suggested in his poster earlier, that spatial stationarity assessment indeed depended on scale, right? So we are going to sort of, we've established that, spatial stationarity assessment depends on scale. So if I'm looking at groundwater data and I'm looking at it for a district in Uttar Pradesh, versus if I'm looking at it for the whole of Uttar Pradesh, or if I'm looking at it for the whole of India, the stationarity assessment will differ. Okay, so every time I have data, let's say it's groundwater data, but I have it for 2 different regions, I have to then source expert domain knowledge to be able to make this decision of stationarity. Thank you for your attention. See you next time.